Yes. So in the last class, we were discussing about what is the instantaneous phase angle for phase modulated signal, and instantaneous phase angle, or yeah, definition of frequency modulated signal that we have seen in the last class. And I'll complete the topic today. Now, just to quickly tell you, what is the instantaneous phase angle defined for phase modulated signal. If I say this is phase modulation, then how did we define the phase modulation phase angle of phase modulated signal? It is phi I of t is equal to what? Phi I of t is equal to, do you remember? Omega ct plus theta naught plus kp into m of t, right? So phi I of t is equal to omega c into t plus kp into m of t. Now, how did we define if you see what is the mathematical structure for an angle modulated signal? If I say S of t is an angle modulated signal, which is defined as AC into cos of phi I of t. Okay, so this is what? This is I can say this is a general template for an angle modulated signal. So angle modulated signal, right? So here I actually have to do what? I actually have to plug in this phi of t here. So what do you get? We will get S of t is equal to AC into cos of omega ct plus theta naught plus kp into m of t. Okay, so this is what? This is phase modulated signal, right? Now, we can do a small assumption here. If we assume, if theta naught is equal to 0, what is theta naught? Theta naught is nothing but initial phase angle at initial phase angle of carrier at time t is equal to 0 is what? Is 0. If we assume that, then what happens? Then what happens is this theta naught, it becomes 0, and hence S of t I can write as AC into cos of omega ct plus kp into m of t, right? So this is a phase modulated signal, right? Now, if you see here, how did we define this? We have defined this phi of t. What is phi of t here? Phi of t is instantaneous phase angle. Instantaneous phase angle. So here, this instantaneous phase angle of phase modulation signal is defined as a function of m of t, or in other words, this phi of t, this phi I of t is directly proportional to m of t. Okay, so this is for a phase modulated signal, right? Now, in addition to this, we had also discussed about frequency modulation definition, right? So how did we define the frequency modulation definition? So if you see that, frequency modulation. So there, you know, in in phase modulation, the phase of the carrier, the phase of the carrier signal is varied with respect to the message signal m of t, right? Let me repeat. In phase modulation, the phase of the carrier signal is varied in accordance with the message signal. Okay. On the similar lines, if I define frequency modulation, in a frequency modulated wave, the frequency of the modulated signal, which means fi of t, is varied in accordance with the message signal, which means I have to vary this as a function of message signal m of t. Now, what is that I have to write here? I have to write this as fc plus kf into m of t, right? fc plus kf into m of t. So what is fc here? fc is the frequency of the unmodulated carrier, and you know uh, that we are adding to, or no, this kf into m of t we are adding to the unmodulated carrier frequency. So this kf, I'll talk about kf and kp in a moment, but what you have to see here is fi of t is varied in accordance with the message signal m of t. Okay, so this fi of t is varied in accordance with the message signal m of t here. Okay. So now the question is, if I wanted to write this angle modulation signal, this is the angle modulated signal, right? So it is s of t is equal to ac into cos of phi I of t. But what is phi I of t for frequency modulation signal? My question is, fi of t I know, but what is phi I of t is equal to what for FM signal? Okay, we don't know this. Okay, all that we know is fi of t only. Okay, now can we calculate phi I of t from fi of t? Can you do that? The answer to this question is yes, we can calculate. Okay, do you, I mean, guys, do you see what is happening over here? See, for a frequency modulation signal, the instantaneous frequency, okay, what is fi of t here? Fi of t is instantaneous frequency. So the instantaneous frequency of the signal should be varied with respect to the message signal m of t, and hence, okay, so actually if I consider a carrier signal, okay, so let me write it here. Let me write here. If I consider a carrier signal, unmodulated carrier, it is AC cos 2 pi into FCT. Okay, this is the actual unmodulated carrier signal. Here, this frequency, if I say it is unmodulated frequency, then FC is constant. It's not going to change. Yes or no? So this is unmodulated carrier. So wherein the frequency is constant. It is not going to change with respect to anything. But in a frequency modulation signal, the carrier frequency FC, it has to be varied with respect to the message signal m of t, which means the frequency, if I say f is, the general, in general, if I write fi, this fi should be varied with respect to the message signal m of t, and hence this fi for a frequency modulation signal was defined as fi is equal to fc plus kf into m of t. So fc is unmodulated carrier frequency, and this plus kf into m of t is added in such a way that this fi is going to change with respect to the message signal m of t. Okay. Now, what is this kf and kp? Okay. So, what is this kf and kp? See, this kp is phase sensitivity of the modulator. Okay. So, in the last class itself, I've discussed these things, phase sensitivity of the modulator, and the units for this are, you have to see what are the units of the remaining things, and based on that you can come up with what are the units of kp. It is measured in, you know radians per volt. Okay. And similarly, kf is frequency sensitivity of the modulator, frequency sensitivity of the modulator. And what are the units? The units are hertz per volt. Okay. So these are the units for the frequency sensitivity. So how did I come up with this hertz per volt or radians per volt? Is very simple. Okay. You see what is the left hand side here? The left hand side is hertz here, right? Left hand side is in hertz. Am I right? And right hand side, if you see, this fc is also measured in hertz because it's frequency, and m of t is measured in volts. Okay. Now the units of kf should be in such a way that this entire thing should be hertz, because I can add only two quantities which are measured in the same units, which means if this is hertz, this also, I mean, the second component here also has to be hertz, right? So which means this kf into m of t should be in terms of hertz, right? Already m of t is in volts, and hence I have to have kf as hertz per volt, such that when I multiply this kf with m of t, this volt and this volt gets cancelled, and I'll be getting the final second part as hertz. Am I clear? So like that, you can come up with just a sec. Just a second, guys. Like that, you can come up with what is kp here. Okay, so left hand side is in radians, and hence this has to be in radians. This also is radians, and I am multiplying with m of t here, which is in volts, and hence this entire thing, actually this entire thing should be in terms of radians, right? Then only I can add that to this radians and this radians. So if this entire thing has to be radians and this is measured in volts, obviously this kp should be in terms of radians per volt. Yeah. Now coming back to the question that I had asked, the question that I had asked was, okay, for frequency modulation signal, I have defined instantaneous frequency as fi of t is equal to fc plus kf into m of t. This is what I have defined. Now, how can I write, the phi I of t? Why I am worrying about phi I of t is because this is the general, template for an angle modulated signal. Am I right? So that's the general template for an angle modulated signal. And there, if you see the template, or if you see the equation there, it is AC into cos phi I of t. AC is anyway AC is anyway the amplitude of the unmodulated carrier signal. It's okay. I mean, I can directly write as it is. What about this phi I of t? Did we define phi I of t for frequency modulation signal? The answer is no, actually, but we have defined only fi of t. Now, from the fi of t, can we calculate phi of t? This is what we have to see now. Okay, so fm frequency modulation So phi I of t, calculation of phi I of t from fi of t. Now, in order to do this, if you remember in earlier classes, we have defined fi of t as, what is fi of t? Fi of t is 1 by 2, 1 by 2 pi into d by dt of phi I of t. This is what we have defined, right? Now, from this, how can I write phi I of t? Phi I of t I can write as 2 pi into fi of t. Let me take one more step back. From this, what I do is I can write this as d by dt 2 pi into fi of t. I can write as what? I can write as d by dt of phi I of t. So all that I done was I just have taken this 2 pi to the left hand side. Now from this again, how can I write phi I of t? Or I can do integration on both the sides. Integrate on both sides. So if I integrate on both the sides, what do we get? I get, you know, right hand side, what I get is phi of t directly, and this side becomes first integration of 2 pi into fi of t dt. It's from 0 to t is equal to, right hand side becomes phi I of t. Okay, or I can say that phi I of t is equal to 2 pi into integral 0 to t into, 0 to t dt, 0 to t fi of t dt. Now, what is this fi of t? For frequency modulation signal, already we have defined fi of t as, can you tell me what is fi of t there? Fi of t was, this is fi of t, right? So which is fc plus kf into m of t. So that I am going to write here, fc plus kf into m of t. So this fc plus kf m of t, I'm gonna substitute this. I'm going to substitute here. Okay. So if I do that, what do we get? So it is phi I of t is equal to 2 pi into integral 0 to t in fc plus kf into m of t dt, right? So I have two terms here. What I will be doing is I'll separate the integration, integral 0 to t, 2 pi integral 0 to t fc dt plus 2 pi into integral 0 to t kf into m of t dt. Now what I will be doing is, first term, fc is a constant, right? What is fc? Fc is unmodulated carrier frequency. Yes or no? Just a second. Just got stuck. Yeah, yes. So 2 pi into, so this fc is constant, which means I can write that outside. Yes or no? Fc is what? What is FC? FC is, let me write it here. FC is unmodulated, unmodulated carrier frequency and which is constant. It's a constant, and hence I can write this FC outside. And when I write the FC outside, I get 2 pi FC into integral 0 to t 1 dt plus 2 pi into what is Kf? Kf is what? Kf is frequency sensitivity of the modulator. Frequency sensitivity of the modulator, and it is also a constant. It's also a constant. Okay, since it is a constant, what I can do, I can write that outside integration, which means 2 pi into Kf into what about m of t? Is it a function of time or not? Yes, it is a function of time, and hence I am just keeping it inside the integration itself, right? So we are almost done. So phi I of t is equal to 2 pi into fc into what is integral 0 to t 1 dt? It is t plus 2 pi into kf into, how can I write this? I cannot write anything until and unless I substitute a special value for no, m of t. So this is the instantaneous phase angle, right? So that's the instantaneous phase angle for a frequency modulation signal, right? So that's the instantaneous phase angle for a frequency modulation signal. Any doubts, guys? So this is what we are willing to derive, right? Now, since I have phi I of t, now how can I write the frequency modulation signal? Therefore, so uh, angle modulation, angle modulated signal equation is what? Angle modulated signal equation is S of t is equal to AC into cos phi I of t. Now what I can do? What I can do here is I can substitute this entire phi I of t, okay, in this particular expression. Okay. So if I do that, what do I get? What I get now is therefore frequency modulated signal can be written as what? It can be written as, I just have to substitute this entire phi I of t in this particular expression. So what I get is S of t is equal to AC into cos of this entire thing I have to write here, which means 2 pi into HCT plus 2 pi into kf into integral 0 to t m of t dt. Okay. So don't be scared by looking at the expression. Okay. So if you just remember this particular fi of t definition, okay, you can derive all these things in 1 or 2 minutes. It won't take much time. Okay. So that's why don't try to mug up anything. Just try to remember this expression as well as this expression. That's it. Once if you remember the definition of phase modulation and frequency modulation, and from the definition itself, you can derive all the things. You need not to mug up anything. Okay. So from the definition of the frequency modulation, we have defined the instantaneous frequency as fi of t is equal to fc plus kf m of t. And from this we have actually defined, sorry, we have actually derived the phi I of t. So this we have seen in one of the earlier classes. And what is phi I of t? Phi I of t is instantaneous phase angle of FM signal. So this is the instantaneous phase angle of the FM signal, whereas in the previous class, sorry, in the previous case, this is instantaneous phase angle of PM signal. So this is for PM signal, and what we are seeing just now, the derivation is for the FM signal. Okay, so this is my S of t. So what is this S of t? This is a frequency modulated signal, and that is nothing but S of t is equal to AC into cos, yeah, cos of 2 pi fct plus 2 pi kf into integral 0 to t m of t dt. Any doubts so far? So finally what I'll write is, if you have any doubts in the derivation, you can ask me, man. Phase modulation signal, S of t is equal to AC cos, what did we write? Omega ct plus kp into m of t. Am I right? So that omega c, I'll just expand it. 2 pi fct plus kp into m of t. This is for a phase modulation signal, and for a frequency modulation signal, S of t is equal to AC into, this is what we just have seen, AC into this expression, okay? Cos of 2 pi fct plus 2 pi into kf into integral 0 to t m of t dt. Okay, so are these are the final expressions for frequency modulation signal and the frequency modulation signal and the phase modulation signal. Okay, so can you just compare, look at both the expressions carefully and see what are the differences that we have. Carefully observe the expressions. Okay, the first one, the phase modulation, is actually a straightforward thing, which means uh, we directly in the phase modulation, we directly define what is the instantaneous phase angle, which means for an unmodulated carrier, what is the phase angle? For unmodulated carrier, the phase angle is directly omega c t plus theta naught. But this is for unmodulated thing. Okay, but we are going to derive, or we are going to do phase modulation, and hence this phase should be varied with respect to the message signal, and hence we have to add one more term here. That term should contain m of t, which means I have to write this as plus kp into m of t. So all, wherever you have kp kf, you just think that they are just some constants. Okay, they are just some constants multiplied with the message signal. So they are the parameters of the modulators, the frequency or the phase modulators that we are going to use in order to generate these angle modulated signals. Okay, so the point I'm trying to tell you is both are, the phase modulation is somewhat a straightforward method, because we will be directly deriving what is the instantaneous phase angle. Okay, so omega ct plus theta naught is unmodulated phase angle, and this plus kp into m of t is added because I wanted to generate a phase modulation signal, which wherein the phase should be varied directly with respect to the message signal. This is what is our interest. Okay, but for a frequency modulation, that's not the case. The frequency should be varied with respect to the message signal, and hence I have to actually define what is the instantaneous frequency. So the instantaneous frequency fi of t is equal to FC is the frequency of the unmodulated carrier, and to that I have to add some one term which actually contains m of t here. Okay, so uh, and hence we have added a term here plus kf into m of t here. Hmm? So kf, as I said again, it's a constant of the it's a constant of the modulator, and this m of t makes sure that the instantaneous frequency is directly proportional to the variations in the message signal m of t. Okay, am I clear, guys? Any doubts? Do you have any doubts? You can ask me. So for a phrase, for a yeah. So for a phase modulation or a frequency modulation signal, after defining the definitions, I mean, after defining the instantaneous phase angle or instantaneous frequency, then you have to see, what is the final expression for the modulated signal. Okay, so this is a general template for a modulated angle modulated signal, wherein I have AC cos of phi I of t. So since I have directly defined phi I of t for a phase modulation, I can substitute that, and finally I can come up with this particular expression. Okay, S of t equal to AC cos omega ct plus kpm of t. But for a frequency modulation, we are defined only fi of t, but not phi I of t. So how to generate phi I of t from fi of t is, by using this particular small derivation. Once if I do that, I'll be getting phi I of t. This phi I of t I have to substitute in the general template for a angle modulated signal, such that I'll be getting this particular S of t. Okay, what is this? This is a frequency modulated signal. Okay, and finally we have written the expressions here. Okay, so these are the mathematical expressions for phase modulation and frequency modulation signals in the time domain. Okay, in the time domain. Now, after deriving these expressions in the time domain, okay, so I have to ask you one following question. The question is, you know, can I generate FM signal using frequency modulation generator, and vice versa? You understand my question? My question is, I have given you a phase modulator. Okay, phase modulator. Okay, but I want the output as FM signal. I want FM signal to be generated. Okay, and what is given to you? I have given only a phase modulator to you. Okay, and similarly, I give you a frequency modulator. What do you mean by phase modulator? Phase modulator is a device which can generate phase modulation signals. Okay, so I give you a frequency modulator, but at the output I want a FM signal. Can I do that? Of course, I'll be giving m of t as input. Obviously, I need m of t, m of t as well as c of t. Both m of t and c of t, I'll be giving it to you. So these are our inputs. Okay, so these are the inputs to you, and I'll be giving you a phase modulator, but you have to produce a FM signal. And similarly, I have given you a frequency modulator, but you have to generate a PM signal. Okay, can we do that? If yes, how? In order to find out the answer, you just have to carefully observe these expressions here. Okay, to be specific, you observe this term and this term. The simple thing I wanted to tell you is, for a phase modulation signal, instead of giving m of t, if I give you input as integration of m of t, then what do I generate? Hmm? Instead of giving m of t as input, if I give you integration of m of t, then what do we get? Can't we get the FM signal? Because if you compare this expression, sorry, this term and this term, what is the difference? What is the difference? One by one, if you see the difference, I have Kp there and I have 2 pi into Kf there. Yes or no? Those are the first differences, right? I have Kp here, I have 2 pi into Kf there. Now, what is the units of Kp? The units of Kp is radians per volt. What about the units of Kf? Units of Kf are, I'm sorry, hertz per volt. But I have 2 pi into, right? What are the units of 2 pi? The units of 2 pi are radians only. So radians into hertz per volt. So it's again, it becomes radians per second per volt. Okay. So here also, what are the units of Kp? What are the units of Kp? Radians per volt. And what are the units of this? Radians per volt.